Welcome back everybody to another video lecture from Ms. Semino. This video is video number 2 in the equilibrium chapter. Today we're going to be talking about Le Chatelier's principle and how to calculate your KEQ or your equilibrium constant. So more specifically, here are some of the objectives we need to be looking at this evening. It says describe how the amounts of reactants and products change in a chemical system at equilibrium. We need to identify 3 stresses that can change the equilibrium position of a chemical equation and explain what the value of KEQ indicates about the position of this equilibrium. So when we're talking about equilibrium, we're generally talking about reactions that are reversible. So some reactions do not go to completion, and we'll talk about this in AP Chemistry, that actually most reactions don't go to completion. There's a lot of reactions that can be reversible. So a reaction in which the conversion of the reactants to the products and the conversion of the products to the reactants occurs simultaneously. So that's what we're talking about if we have a reversible reaction. So we can look down here, we've got our sulfur dioxide, 2 moles of sulfur dioxide plus 1 mole of oxygen is going to yield 2 moles of sulfur trioxide. But if we look at this arrow in the second one here, this actually is a reversible reaction. So our sulfur trioxide could actually decompose back into its original ingredients of sulfur dioxide and oxygen. So this is a reversible reaction. So we saw this earlier this year that if we have this double arrow here, this can indicate, and I should say the double arrow here, this can indicate that it is a reversible reaction. I always joke that chemists, we like to write as little as possible, so notice that by using this double arrow, we're not having to write that second equation, chemical equation, like we did on that previous slide. So an important key concept here is a chemical equilibrium occurs and there's no net change occurring in the actual amounts of the components of this system. So we talked a little bit about something called a dynamic equilibrium before. So basically what this is saying is you might not have equal amounts of these, but the amount that are going in this direction is going to be equal to the amount going in this direction, and this is where we've established that chemical equilibrium. So reversible reactions, it says here that even though the rates of the forward and the reverse reactions are equal, the concentrations of the components on both sides may not be equal. This is what I was just mentioning. So we could have an equilibrium of having 1% and 99%, or 99% and 1%. So note the emphasis of the arrows of the direction. It depends on which side is favored. Almost all reactions are reversible to some extent. So here we are to Le Chatelier's principle. You'll find different teachers pronounce this different ways, but we're going to see that this is the main principle we use in equilibrium. And this principle comes from Henri Chatelier. He studied how the equilibrium position shifts as a result of changing conditions. These changing conditions we're going to call stresses. So the Le Chatelier principle says if a stress is applied to a system in equilibrium, the system changes in a way that relieves the stress. So here are the 3 things that can stress a system. We can have concentration, temperature, or pressure. So concentration. So adding more reactant produces more product, and removing the product as it forms will produce more product. So temperature is kind of a tricky little stress. So it says here temperature. Increasing the temperature causes the equilibrium position to shift in the direction that absorbs heat. So if the heat is one of the products, just like a chemical, it's part of the equilibrium. And this is what I do, is I try to treat heat just like a product or a reactant, depending where it is. And so just like we said a second ago, if we increase the reactants, it'll shift it towards the products. If we reduce the products, we will shift it towards the reactants. So treating heat like a product or a reactant can help us make predictions. It says here, so cooling an exothermic reaction will produce more product, and heating would shift the reaction towards the reactant side. So here is our equilibrium, here's our reactants, here's our products. So if we heated it up, we'd be adding more heat. So this reaction would shift in this direction. On the other hand, if we cooled things down, we would be making this smaller, this value smaller, so it would shift in this direction. Hopefully you guys can see that arrow there. Pressure is also another tricky one for kids. So pressure, meaning that we change the pressure, will only affect gas equilibrium. So we only have to worry about equations that have gases in them. So increasing the pressure will usually favor the direction that has fewer molecules. So if we were to increase the pressure in this reaction shown here, you can see that we've got 1 mole and 3 moles, so 4 moles on this side, or we can say molecules, remember, and this one only has 2. So if we increase the pressure, we would shift it this way. So that means that for every 2 molecules of ammonia made, 4 molecules of the reactant are used up, and in this equilibrium it's going to shift towards the right with an increase in pressure. So you might wonder why that is. Well, if we're increasing the pressure, you want to try to get to a point where your pressure is at equilibrium. So if you increase the pressure, you really then want to figure out some way to reduce the pressure. So remember how we measure pressure. We measure the number of collisions or the strength of those collisions. So the way to reduce the pressure then would be to have fewer collisions. So if you had fewer molecules, you would therefore have fewer collisions, and that's why this one is going to move in this direction. You're going to go from 4 molecules that can hit each other to only 2 molecules that can hit each other, and that will reduce the pressure. So now we finally get to our, we finally get to our KEQ value, and this is known as our equilibrium constant. We like equilibrium constants because it's a numeric value, not just a percentage, and we can use this to compare different equilibrium expressions and make predictions about whether the products or the reactants of a reaction are going to be formed. These values are based off of the amounts or the molarity, I like to say the concentration of the reactants and the products, and so again it's called the equilibrium constant and it's abbreviated with our KEQ. Okay, so now we're going to learn how to calculate that numeric value of our KEQ, our equilibrium constant. So here it says, consider this reaction. The capital letters are the chemical and the lowercase letters are the balancing coefficients. So we've got our coefficient of lowercase is our coefficient, this is our chemical coefficient, chemical, and so on. So the equilibrium constant KEQ is a ratio of the product concentrations to the reactant concentrations at equilibrium, with each concentration raised to the power, which is the balancing coefficient. So let's see how this looks. So again, we've got this equation here. And so the way that we would set this up is we'd put our products over our reactants here to get our KEQ value. So these little brackets here mean concentration. They're kind of just a short way of saying that. So notice that you've got your chemical on the inside here being raised to the power of its coefficient. One thing to note here, and you guys know that I'm a stickler for units, you'll be happy to know though that KEQ has no units because it's a ratio. These units are actually canceling each other out. So as I mentioned, the KEQ value or the equilibrium constant can give us some information about whether the products or the reactants are going to be favored. If your KEQ value is greater than 1, the products will be favored. If your KEQ value is less than 1, your reactants will be favored. So here's one of those example problems. So go ahead and take a minute and look this over. We're looking at this equation here. They're telling us that we have a specific amount of our nitrogen dioxide and our dinitrogen tetraoxide here. So if we go ahead and we'll set up our equilibrium expression, it'll look something like this. So our KEQ, our nitrogen dioxide is our product, so that's why it's going on the top. Notice up here it has that coefficient of 2, so that's why it's being raised to the power of 2. Then our reactant is our dinitrogen tetraoxide. It goes on the bottom. There's no coefficient there, so that's just raised to the power of 1. So we want to go ahead and plug in the concentrations that we have, and up here we had our knowns and our unknowns. So our concentration of our dinitrogen tetraoxide will go on the bottom. Our concentration of our nitrogen dioxide will go on the top. Notice this top one we're squaring though because it had that coefficient of 2 here. So when you go ahead and do the math, we're going to find out that our KEQ has a value of 0.2. This means that our reactants are going to be favored because this value is less than 1. So we'll be doing some more practice in class using Le Chatelier's principle and predicting which direction a reaction will occur due to those stresses. And then we'll also be setting up some more of these equilibrium expressions. If you guys could just try to remember the general format where we've got our products over our reactants and the exponent there is representing the coefficient that was in our chemical equation. I hope this video was helpful, you guys. Remember to write down any questions you have, and I'll see you in class. Bye.